Welcome everyone to this new video. In this video we're going to learn about evaporation, and for this video we only have two problems, and let's start with them. 4.2. Imagine you are in charge of managing a big reservoir. People downstream need a steady supply of 48,000 cubic meters per day during July to meet their needs. So we have the reservoir here. I have an image that will represent this problem. We have a reservoir, you're in charge of it, and how much water you need to um, release, because downstream, farther down, it's needed 48,000 cubic meters per day of water. To figure out how much water to release from the reservoir, you need to consider water loss due to evaporation. You know the daily evaporation rate from the Class A pen is 5 millimeters per day, but this tool overestimates actual evaporation, so you'll use a correction factor called a pen coefficient of 0.7. Um, the river carrying the water from the reservoir to the people downstream is 61 meters wide and stretches 78 kilometers long. So far we are given that about 5 millimeters per day of water is evaporated, and we're given, let's say this is a river here that takes the water downstream. This river is given, we're given that is 61 meters wide and 78 kilometers long. Now your job is to calculate how much extra water you need to release from the reservoir to account for water loss due to evaporation. Determine the total amount of water in cubic meters and acre feet you need to release each day to meet the downstream demand. These two parts are pretty much the same. We need to find out how much water in cubic meters and acre feet water volume we need to release. And since we want 48,000 cubic meters downstream and we're going to be losing some of it due to evaporation, we have to release even more than 48,000 cubic meters to account for the water loss. Important notes, let's say, we are assuming that the amount of water soaking into the ground, infiltration, and the amount of water used by plants, transpiration, is very small and can be ignored. So obviously on the river channel, the water is being infiltrated and is going to groundwater, but in this problem that's so minimal that we can ignore it. We're also assuming that the river doesn't change its shape or depth as the water flows downstream. Obviously, we know that that's not true, but we're gonna treat this river as a channel where water doesn't infiltrate and its cross-sectional area doesn't change either. So let's get started. So with the values that we have, first let's find out how much water actually is being evaporated, the rate of evaporation. And if we remember from our equation, the evaporation is equal to the coefficient, which is 0.7 we're given, and it measures 5 millimeters per day. So the evaporation is gonna be actually 3.5 millimeters per day. Let's convert this to meters. So in 1 meter there are 1,000 millimeters. So millimeters cancel, and we're gonna end up with 0.0035 meters per day. This will be our actual evaporation rate in meters per day. Now let's find out what the actual area of our river is, and that's gonna be the width, 61 meters, times its length, that is 78 kilometers. Let's convert the kilometers. Should have not used. Let's convert the kilometers to meters. That was 61 meters times 78 kilometers, and there are 1,000 meters in 1 kilometer. Cancel kilometers. That's gonna give us approximately 4.758 times 10 to the 6 square meters, and that's the area. Now let's find out. We have the evaporation that happens per day in depth, just meters. Let's find out the volume of the evaporation. So the evaporation as in volume is gonna be those 0.0035 meters per day times the area 4.758 times 10 to the 6 square meters, and that's gonna be about 16,653 cubic meters per day. So that's the volume of water that's being evaporated every day. Now we are being asked for determine the total amount of water you need to release. So per day, let's see, you need to release each day. So if this is the amount of water lost and we need 48,000, so we just need to release those 16,653 plus the 48 that we need cubic meters per day. So we need to release about, what is that, 64,653 cubic meters per day. So this is one of the answers in cubic meters per day. Now we need to convert that into acre feet per day. So to do that, we're gonna use 64,653 cubic meters per day times we need to cancel the cubic meters. So in 1 meter we have 3.28 feet cubic, and then we need to cancel this feet here. We need to cancel it and we make it an acre. So 1 acre 43,560 square feet. So we have cubic meters here. This is gonna be cubic meters. So this is gonna be cubic feet in square. This is, so we only have feet, acre feet per day. So this is going to give us a value of about 52.37 acre feet per day, and these two values represent the same amount of water, just in different units. And that's it for this problem. So let's move on to 4.3. In 4.3 we are asked, estimate the mean monthly evaporation rate for the O'Hare International Airport watershed in Illinois. Local climatological data supplied by NOAA for the airport are shown for months in the year 1974. So what is that saying is, this is the precipitation, this is supplied by NOAA, how much water is raining per month in the year of 1974. Now, the water leaving the watershed is estimated from the U.S. Geological Survey gauging, or USGS gauging station, and is also shown. This is the data retrieved from the USGS gauge at that station. Comment on your answers by explaining why the results are low relative to the annual average values given in figure 4.3. This is figure 4.3. This is a map of the average annual lake evaporation data in centimeters between 1946 and 1955. So our gauge is going to be somewhere in here. What assumptions have you made? Assume storage changes are minimal and no transpiration or infiltration. So let's make this bigger, smaller, put it somewhere here. Gonna use it later. So what's happening here, we have, let's say, we have a watershed. Okay, this is our watershed, and just here I'm trying to draw the, I don't know, the terrain, the underground. This is the surface. Anyway, so what's happening is we have, let's say in March, 2.4 inches of precipitation. So let's say it rains, and what rains is 2.4 inches, and the outlet, let's say the outlet is down here. What the gauge, the outlet is recording is only 1.42 inches. So the difference between these two values is being lost. It might be lost due to evaporation, because that's the topic of this video. It could also be lost through infiltration or transpiration, other reasons, right? But in our problem, it says assume storage changes are minimal and no transpiration or infiltration. So we are treating this watershed as if it was like glass. There is no other losses than evaporation. So with that said, now we need to find, we need to solve for, we are asked for the water loss each month, right? Where is that? We are asked to estimate the mean monthly evaporation rate. So all we need to do is subtract this value minus this value, and that's what is being lost. And I assume that's 122. Yep. So these are the inches lost in evaporation. So now that we have the values that are evaporated each month, we need to solve for the mean monthly, which is just the average of all these values. Average. So 1.238 inches is the mean monthly. So in average, each month we lose about 1.238 inches of precipitation of water. Now we need to compare this value, 1.238 inches, to what this graph here, the figure 4.3, says it's actually lost. And that gauge is about in this area here. So if we follow that curve, we say that we have 76, remember this is in centimeters, of water evaporated every year. So let's convert those 76 centimeters into inches to get a better idea. And this is centimeters per year, in total per year. So in 1 year we have 12 months multiplied by, in 1 inch, have 2.54 centimeters. So centimeters cancel, year cancel, and we have at the end 2.49 inches per month. You remember, if you see, we have 1.38 inches also per month, right? So our value is way less, almost half, if not half, of what it says in this figure. We need to explain what assumptions and why we think that that's the case. I can think of two reasons. One of them is I noticed the year. This is from 1974, and this graph is 1946, 1955. So I don't know, maybe later in time, some, I don't know, some is stronger, and global warming, more water is evaporated. Or another reason could be that since in our case we are saying that none of the water, actually in our case we are making these storage changes minimal and no transpiration or infiltration. Who knows, maybe that plays something in this situation, and that's why our value is actually less than what this figure shows. It might be also with the land cover use, like the type of land might have changed, or new developments and stuff like that. So these are some of the reasons that can make that these two values make them different, right? So yeah, I hope this video is helpful for you, and I'll see you in the next video.